You think time just flows forward, past, present, future, one direction, always forward, never back. Obvious, right? That is just how it is. Time moves forward. Everyone knows that. But why? What makes time go forward? What stops you from going back? Most people have never really thought about this. They just accept it. Time goes forward. That is life. That is reality. But that is not an answer. That is just describing what you see. When you really ask why time has a direction, when you dig into what is actually creating this arrow, you discover something so strange, so profoundly different from what you'd expect. It shatters everything you think you know about cause and effect. The direction of time isn't built into the laws of physics. It is not a fundamental rule. It is something else entirely. Something that emerges from chaos, from probability, from the simple fact that there are more ways for things to be disordered than ordered. Let me show you what I mean. Let's start with something simple, something everyone has experienced. You drop a glass, it shatters, pieces everywhere. You've seen this 1,000 times now. Have you ever seen the reverse? Have you ever seen broken glass spontaneously reassemble itself? Jump off the floor, fly back together, form a perfect glass again. Number never. It doesn't happen. But here is the thing. If you look at the fundamental laws of physics, the equations that govern how particles move, how forces work, there is nothing in those equations that says this can't happen. Newton's laws work backwards, just as well as forwards. If you film a planet orbiting the sun and play it backwards, it still obeys Newton's laws perfectly. The equations don't care which direction time goes. Same with Maxwell's equations for electromagnetism. Same with quantum mechanics. Same with Einstein's relativity. All the fundamental laws of physics are time-symmetric. They work the same forwards and backwards. So why doesn't the glass reassemble? If the laws of physics allow it, why doesn't it happen? This is the puzzle. This is what kept physicists up at night for over a century. The answer comes from a man named Ludwig Boltzmann. And what he discovered is so simple, so elegant, that when you first hear it, you think, that can't be all there is to it. But it is. Here is what Boltzmann realized. Let's say you have a box, and in that box, you have gas molecules. Just tiny particles bouncing around. Now, there are many, many ways these molecules can be arranged. They can all be in one corner. They can be spread out evenly. They can be clustered in the middle. Endless possibilities. But here is the key insight. There are far, far more arrangements where the molecules are spread out evenly than arrangements where they're all clustered in one corner. Think about it. If you have 100 molecules, there is only one way for all of them to be in the exact same spot. But there are trillions upon trillions of ways for them to be spread throughout the box. So if these molecules are just bouncing around randomly, what is going to happen? They're going to find themselves in one of the spread out arrangements, not because there is a law forcing them to spread out, but because there are so many more spread out arrangements than clustered arrangements. It is probability, pure statistics. This is what we call entropy. Entropy is a measure of how many different arrangements a system can have. High entropy means many possible arrangements. Low entropy means few possible arrangements. And here is the rule that emerges. Systems tend to move from low entropy to high entropy, from few possible arrangements to many possible arrangements. Not because of any fundamental law, but because there are simply more high entropy states than low entropy states. The glass shattering, that is low entropy going to high entropy. There are far, far more ways for the glass to be broken into random pieces than there are for it to be assembled into one perfect glass. So when it shatters, it is finding one of the overwhelmingly more numerous disordered states. Could it spontaneously reassemble, in principle? Yes, the laws of physics allow it. But the probability is so stupendously, incomprehensibly small that you could wait longer than the age of the universe and never see it happen. This is the arrow of time. Time appears to flow forward because entropy increases, and entropy increases because there are more disordered states than ordered states. But wait, let's think about this more carefully. If the fundamental laws are time-symmetric, if they work the same forwards and backwards, then why does entropy increase in one direction? Why doesn't it increase in both directions? Good question, really good question. This is where things get truly strange. Imagine you are watching a movie of gas molecules in a box. At the beginning of the movie, all the molecules are clustered in one corner, As time goes on, they spread out. Eventually, they're evenly distributed throughout the box. No, play the movie backwards. At the beginning of the backwards movie, the molecules are evenly distributed. As time goes on backward, they gather together into one corner. Both directions show entropy increasing from your perspective as you watch. Going forward, they spread out. Going backward, they also spread out from the clustered state you started with. But wait, that is a trick. In the backward movie, we started with the molecules evenly distributed. That is actually the high entropy state. So playing backwards, we're going from high entropy to low entropy. We're watching entropy decrease. And that looks weird. That looks wrong. That looks like time running backwards. This is the key insight. The arrow of time is tied to the initial conditions. If we start with a low entropy state, entropy will increase. Time will appear to flow in that direction. But why did we start with a low entropy state? Why was the universe in a low entropy configuration in the beginning? That is the real question. That is the mystery. And nobody knows the answer. Not really. We know the universe started with the Big Bang. We know it was in an incredibly low entropy state back then. Everything was smooth, uniform, hot. But that is actually low entropy because gravity was involved. And for gravity, having everything spread out uniformly is a low entropy state. As the universe expanded, as gravity pulled things together into stars and galaxies and black holes, entropy increased. And it is still increasing now, and it will keep increasing until everything reaches thermal equilibrium, until every bit of usable energy is gone. The heat death of the universe. But why did it start in a low entropy state? Why wasn't the universe born in a high entropy state, already at equilibrium? We don't know. This is one of the deepest unsolved questions in physics. Some think it has to do with the specific conditions of the Big Bang. Some think it has to do with quantum mechanics and the wave function of the universe. Some think there might be many universes, and we happen to be in one that started with low entropy, because those are the only ones where observers like us can exist. But nobody really knows. It is a mystery. Now, let me show you something even stranger, something Feynman talked about. Let's think about a single particle, an electron, say. In quantum mechanics, we describe particles with wave functions, and the wave function evolves according to the Schrödinger equation. Here is the thing. The Schrödinger equation is time-symmetric. If you have a wave function that evolves forward in time, you can run it backwards, and it still obeys the equation perfectly. So at the quantum level, at the level of individual particles, there is no arrow of time. Time is completely reversible, but we see irreversibility everywhere. We see entropy increasing. We see time flowing forward. So where does the irreversibility come from? It comes from measurement, from observation in quantum mechanics. Before you measure a particle, it exists in a superposition. It is in many states at once. All possibilities are real until you look. But when you measure it, when you observe it, the wave function collapses. The particle becomes one definite thing, one definite state, and this collapse is irreversible. You can't uncollapse a wave function. Once it is collapsed, it is collapsed. This is where irreversibility enters at the quantum level. Not in the evolution of the wave function, that is reversible, but in the measurement, in the interaction with a macroscopic system. And here is where it connects back to entropy. When you measure a particle, you are entangling it with a huge system. The measuring device, your eyes, your brain, the environment. And that huge system has enormous entropy. It has countless degrees of freedom. And once the particle becomes entangled with that system, the information about its quantum state gets scrambled, gets spread out among all those degrees of freedom. You can't reverse it because you can't track all those degrees of freedom. You can't undo the scrambling. The information is still there. In principle, the evolution is still reversible in principle, but in practice it is lost. It is irreversible. This is called decoherence, and it is how quantum mechanics connects to thermodynamics. It is how the reversible laws at the quantum level give rise to irreversibility at the macroscopic level. Feynman understood this deeply. He understood that the arrow of time emerges from statistical mechanics, from the fact that there are more disordered states than ordered states. But he also understood something else, something profound. The arrow of time is not absolute. It is not fundamental. It is emergent. It arises from our perspective, from our interaction with the world. If you could track every single particle, every single degree of freedom, you would see that the fundamental laws are still reversible. The arrow of time would disappear. But we can't do that. We can't track everything. We're macroscopic beings interacting with macroscopic systems. We see averages. We see statistical behavior. And from that perspective, time has a direction. Entropy increases. The past is different from the future. But it is not because of any fundamental asymmetry in the laws. It is because of the initial conditions and our perspective. Now, let me tell you about something even more mind-bending. Something that really shows how strange this is. Imagine you have a box of gas. All the molecules are in one corner. Low entropy. You wait, the molecules spread out. High entropy now, you might think. Okay, entropy always increases. The molecules will never gather back in the corner. But that is not quite right. Given enough time, any configuration will eventually recur. If you wait long enough, purely by random chance, all the molecules will happen to be back in that corner again. How long would you have to wait? An unimaginably long time, far, far longer than the age of the universe. But it is not impossible. It is just incredibly improbable. This is called a Poincaré recurrence, and it shows that entropy doesn't increase forever in a closed system. It fluctuates. It goes up and down. But the fluctuations down to low entropy are so rare that we never see them. But here is the really weird part. If you wait long enough for a Poincaré recurrence, if you wait for the molecules to spontaneously gather in the corner again, what happens to the arrow of time? It reverses. From the perspective of someone inside that box, as entropy starts increasing again from that low entropy state, time would appear to flow forward in that direction. The arrow of time is local. It is tied to the entropy gradient. It points in the direction of increasing entropy. So in principle, you could have different regions of the universe with different arrows of time. If some region fluctuated to a low entropy state, time would flow forward from that state, and it might be in the opposite direction from our arrow. We don't see this because the whole observable universe is in a state of increasing entropy from the Big Bang. We all share the same arrow, but it is not fundamental. It is contingent on the initial conditions. This is what Feynman meant when he talked about the arrow of time. It is not a law. It is an emergent phenomenon. It arises from statistics and perspective. Now, you might be thinking, but I remember the past. I don't remember the future. That is real. That is not just statistics. True memory is directional. You remember what happened before, not what happens after. But why? Why does memory work in one direction? Because memory is a physical process. To remember something, you have to encode it. You have to create a record, a pattern in your brain. And creating a record increases entropy. You are taking a blank slate and writing on it. You are going from fewer possible states to more possible states. So memory itself is tied to the arrow of time. You can only remember in the direction of increasing entropy because memory formation increases entropy. If entropy were decreasing, you wouldn't be able to form memories, or rather, memories would be erased as entropy decreased. This is why you can't remember the future, not because the future doesn't exist, not because time fundamentally flows forward, but because the physical process of memory formation is tied to entropy increase. It is all connected cause and effect. Memory, the arrow of time, all emergent from the same statistical principle, more disorder than order. Let's bring this all together. Why does time have a direction? Because entropy increases. Why does entropy increase? Because there are more high entropy states than low entropy states. Why did we start in a low entropy state? We don't know. That is the mystery of the Big Bang. The fundamental laws of physics are time-symmetric. They don't distinguish past from future. But the universe started in a special low entropy state, and from that initial condition, entropy has been increasing ever since. And that increase in entropy, that movement from order to disorder, is what gives time its arrow. It is what makes the past different from the future. It is what creates cause and effect. It is not a fundamental law. It is an emergent phenomenon, a statistical fact, a consequence of probability, and yet it is one of the most profound features of our universe. It is why we exist. It is why we can think. It is why we can remember. It is why anything happens at all. Without the arrow of time, without entropy increasing, there would be no change, no life, no thought, no us. The universe would be frozen at equilibrium. Nothing would ever happen. But because the universe started in a low entropy state, because entropy increases, time flows. Change happens. Life emerges. We exist, and the beauty of this. The profound beauty is that we can understand it. We can trace it back. We can see how it emerges from simple statistical principles. Boltzmann figured this out in the late 1800s. He saw that entropy was about counting states, that the second law of thermodynamics was really a statistical law, not a fundamental one, and people mocked him for it. They didn't believe him. They thought he was wrong. He struggled with depression. He eventually took his own life. But he was right. He was absolutely right, and now we know it. We've tested it. We've confirmed it over and over. The arrow of time is statistical. It emerges from probability, from the simple fact that there are more ways to be disordered than ordered. And this understanding opened doors. It connected thermodynamics to statistical mechanics. It laid the groundwork for quantum mechanics. It shaped our understanding of cosmology, of black holes, of information theory. This is how science works. Someone has an insight. It seems crazy. People resist it. But if it is right, if it explains things, if it makes predictions that come true, then eventually it is accepted. And then it becomes the foundation for the next insight, the next discovery, the next breakthrough. That avalanche that started with Newton, that continued with Boltzmann, that is still going today. We're still discovering, still learning, still uncovering the deep structure of reality. And the arrow of time, this simple fact that time flows forward, turns out to be one of the deepest mysteries. Not because it is complicated, but because it is so simple that we almost missed it. It is not in the laws. It is in the initial conditions. It is in the statistics. It is in the overwhelming probability that disorder beats order. That is the answer. That is what Feynman discovered, what Boltzmann discovered, what we now know. Time has a direction because the universe started in a special state, and everything since then has been sliding toward equilibrium, toward maximum entropy, toward disorder. And we're riding that wave. We exist in the middle of that slide, in the brief window where there is enough order to create structure, to create stars and planets and life and thought. Eventually, it will all end heat death. Maximum entropy, no more change, no more time arrow. But that is trillions of years away. For now, for as long as we exist, time flows forward, entropy increases. The arrow points one way, and we get to experience it. We get to understand it. We get to marvel at how something so fundamental, so seemingly obvious, emerges from something so simple. That is the beauty of physics. Not comfort, not simplicity, truth.